So far, we've seen how to compare different acid strength based on looking at their conjugate bases and the stability of the conjugate bases. So, more stable conjugate bases were associated with stronger acids, but the problem with that method is that it doesn't let us tell whether the conjugate base is more stable if we have more than one thing going on. So, if we take a look at this example down here, we have an H that's attached to an oxygen. So when that gets removed, we're going to have a negatively charged oxygen. That's going to have resonance stability in this ring because we do have a pi bond next to those lone pairs that would be produced. And then in this other one, we're dumping the electrons onto a carbon, so a different atom, also a different hybridization because it's in a triple bond. And so we have a lot of different things going on with these examples. When that's the case, what we have is a pKa chart that we can consult, and these are values that are actually measured for certain acids or certain functional groups. And so the pKa values basically tell us how acidic a proton is. And a lower pKa value is associated with a stronger acid, and that's the important thing to remember for reading the pKa values. So we're going to use them from the chart. There are a variety of charts. Here's one that will deal with a lot of the molecules we're going to deal with in our class. And so the first couple we can see, the first few pKa values listed up to about this point are all ones that you can just look at and read off of the table. So this isn't bad for these ones here because they're going to not really vary that much. These are specific values for specific species. Where it gets a little bit more difficult to read pKa tables, although it doesn't sound like it would be that hard, is when it gets to the compounds down here that have some abbreviations. We have some more generalizations for the functional group. So an R group is an alkyl group. So that ROH, for example, could be something like an ethyl group. It could be a methyl group if we only had a CH3 here. It could be longer than this. Any kind of alkyl chain is associated with that. So if we have any kind of alkyl chain, this H has a pKa around 16. And so that's how we would read that. What's different between ROH and AROH, we have our alkyl and our aryl. Our aryl group is going to be an aromatic ring. So this would be something like what we actually have in our problem. And the reason that this is different is because of that resonance possibility. So these ones, we see that actually the pKa is lower than the alcohols with just an R group attached. And that does make sense based on what we know about the conjugate base stability. We would expect this conjugate base to be more stable than dumping the negative charge onto this oxygen because this one can actually do resonance into the ring. So we do expect this one to have a lower pKa value because we expect its conjugate base to be more stable than this one up here. And so that AR part is there. And then this is what we refer to as R. So R is strictly just alkyl. And so we see that in a few of our examples. We have ROH, RSH, so same kind of thing, alkyl, and then an SH, alkyl, and then an NH2. And then we have an aryl, like we have here, but with an SH, and then an aryl with like a CH3. So if this was a CH3 instead. The other one that can be a little bit hard to read is the RCOOH. That one, it has a few different abbreviations. We could call it RCO2H. Really what that looks like is this. So what we're dealing with is a carboxylic acid. So it's important to know that that's what that RCOOH is referring to as a carboxylic acid. There's a few different ways to abbreviate the carboxylic acid group, and so we see that here. We see that that pKa is relatively low, and if we think about this one compared to the one up here, that does make sense because we do have that resonance. We're also on top of that pushing that negative charge onto a more electronegative atom than we would in, for example, this case up here. So we do expect that to be lower just because of that as well. And so that's a better acid. We have water that we can read right from the table. We have these few compounds. And then what we have and what's important for our example that we had on the previous slide is this group here. So we have H on the triple bond. We could also have the R group there. They're going to be very similar. And so that exact example, we're looking for as similar as we can get on this table, which is going to be, for our example, is going to be this triple bond up here because we're taking the H that's directly attached to the carbon there. And so that's going to be important for our example. So this 25. And then for the other molecule we had in our example, we had this structure, which is an AROH, which should be about 10. So this one has a lower pK than the alkyne H, like this one. And so we're expecting this compound to be a stronger acid than the one that we had on the previous slide. And so that's kind of how we read this table. We have some other values for H is attached to a carbon of a double bond, H is attached to just a carbon in a single bond. And we see that these values actually follow what we learned about hybridization, because that's what's changing between these three. We see that we saw that sp3 were kind of the least stable for putting the electrons into the sp3 orbital because they're farther away from the nucleus, versus the sp2 versus the sp was the best, and so therefore it has the lowest pKa for the corresponding acid. We also have some important positively charged oxygen species here and here, and then our carbonyls there that we'll examine in a little bit. So going back to the question, wrote out the pKa's that we got from the table. We had the AROH value that we used for to find out that pKa was 10, and then we had our alkyne. We used this one was the exact one on the table, but it's very close because we still have that H bound to a triply bound carbon there. So we use that pKa of 25, and so lower pKa is going to be a stronger acid, and so in this case, this is going to be our stronger acid because it has a lower pKa. How is this going to relate to another type of question with the equilibrium? We can definitely use this to tell, first of all, if a reaction will even happen in acid-base reaction. So if we wanted to know if this reaction will happen where this oxygen takes the H from the HCl, if that's even possible, we're going to be able to tell by the pKa values. And so let's first draw our mechanism like we normally do. So in order for this to happen, we would have to have the oxygen grab the H and put the electrons onto the chlorine. That's our mechanism. When we're going to look for pKa values, what we're going to look for is the values for the acids. And so that's how it's different than when we are dealing with conjugate bases. We are looking at the one conjugate base versus the other. In this case, they're so different. We have a negatively charged chlorine, we have a neutral oxygen. So where do we even start to compare the conjugate bases? This is when it suggests to us that we go to that periodic table, or sorry, the pKa table, to figure out which acid is going to be stronger. And so when we're thinking pKa's, we're going to have to figure out which ones are acid, which ones are conjugate acid, because those are the ones we're going to be comparing the values for. So in this reaction, the acid that gave up its proton, HCl, the base that took it was the carbonyl, actually, the C double bond O compound. Our conjugate acid is the one with the proton on the other side, so that's going to be the first species, and then our conjugate base is the chlorine. And what we're going to compare for the pK values is the acid and the conjugate acid. So we're going to be looking at our table for HCl, which we should be able to read right off the table, and a species that looks like this. So our HCl right here, pK of -7. Our carbonyl species, we see that over here. This is a general species, but we still have the hydrogen attached to that positively charged oxygen, -3 pK. So we have these two values for our pKa's. We are going to, the equilibrium will favor the weaker acid, so the one with the higher pKa. And when we're dealing with negative values, it can be a little bit harder to see, but the -3 pK is a higher pK than -7, and so we're going to favor the products in this case. So we're looking for that higher pK because that's a weaker acid. It's not going to be as willing to give up its proton, not as reactive, and so the equilibrium is going to be more stable on the side with the higher pK. And so what we did here, we looked at the pKs, we went with the higher one. That's the side the equilibrium is going to be favored. We're going to actually see this type of transformation in the next chapter with the reactions that we're going to be talking about with the carbonyls, and so that's kind of why this specific example was chosen here.